welcome to RF transceiver design course. We are discussing about the mixer design, and in last class we have seen widely used mixer, which is a Gilbert cell mixer. We have also done the analysis of balanced mixer by using a hybrid coupler. We have also done analysis of a single balance, double balance mixer, and how the gain can be calculated, conversion gain. Now, in this class we will see the passive mixer, which is widely used in the RF transceiver design. So, we have already done the base of understanding the passive mixer. So, what does it mean by passive mixer? Where we do not use any external bias, means VDD, we do not give a VDD, only by switching you will get the conversion gain, conversion loss. So, in mixer there is a conversion loss, there will not be any conversion gain. So, we have already done the analysis that if there is a switch and if switch has a square input and if this is a RL resistance, then we can find out the this is a VLO, LO voltage, and we have already discussed this is a Fourier expansion of the square wave. It can be expanded into 1 by 7, 1 by 9 for all the harmonics, but if we consider up to fifth harmonic, and when it is multiplied with the RF signal cos omega RF t, you will have a 2 by pi A RF cos omega LO minus omega RF t, a 1 by 3 cos 3 omega LO minus omega RF t. So, here the your gain is 2 by pi. So, in this case this is for passive mixer, the conversion loss is given by 2 by pi. So, that is directly can be calculated from this, and here we have used the resistance. So, there are two kind of passive mixer. One passive mixer is a return to 0 RZ and another is a NRZ, non return to 0. So, what does it mean by return to 0? Because here resistor RL is connected with the ground, it is considered as a return to 0. Now, instead of a resistor, if we use a capacitor here, then it is a non return to 0, because capacitor is going to hold certain voltage for some duration until unless the switch will not be the on. So, that is a separate mixer, the passive mixer, which is called a non return to 0 mixer. So, we can classify passive mixer in two types, one is a return to 0 and another is a non return to 0. Now, we will try to understand that how the noise will how noise perform in this passive mixer. So, if we consider the noise source, that is source voltage Vn Rs, and this is a ground. So, we need to consider the Rs, and here this is a switch, we are considering it is ideal switch, and this is a RL. So, here RL is much greater than Rs, that we are considering. So, what will happen, that whatever noise which is generated by the Rs will be switched, and that will have a that will supply to the RL. So, what will happen, that we already have seen the noise generated by Rs is given by 4 kT Rs, and this 4 kT Rs noise is divided in both upper sideband and lower sideband. So, we can consider the noise contribution of the RS in mixer is a 2 kT RS. So, here the single sideband noise is given by a 2 kT RS. Now, we if we try to find out the if it is in time domain, there is a random noise voltage. So, the noise voltage is random, and then there is a square wave that is a multiplied. So, now this random noise we can represent in terms of the frequency domain, that is a 2 kT RS, and this will be convolved with the equivalent sinc kind of function, and it has a different amplitude. This is at 0, then there is a plus FLO, minus FLO, then at third there is a third harmonic minus 3 FLO plus 3 FLO. So, this is how the when we try to do the convolution. So, this is a convolution, and this is equal to, we need to find out. So, if we consider this Vn square out equal to 2 kT RS into, if we use the same Fourier series 1 by 2 square, only consider the amplitude 2 by pi square, 2 by 3 by 3 pi square plus 2 by 5, and it will go on like this. Now, if we take this common, again it will be the Fourier series 1 plus 1 by 3 square plus 1 by 5 square plus, it will go on. So, here we can consider this the final output is equivalent to the 2 kT RS. So, the output also has a noise which is a 2 kT RS. So, single sideband version. So, if we consider this is a single sideband noise, if we consider the double sideband, it will be the, so we already have discussed that the double sideband is a 2 times of, so we can consider the single sideband noise as a kT RS. So, this is how the noise can be calculated, and so this is for 2 sideband, and then so 2 sided output spectrum is equal to kTRS, and the one sided spectrum, so this is a one sided spectrum which is a 2 kTRS, that is on the one side, and double sideband is a considered as a twice of that. Now, we can also make a single balance version of the same. Single balanced passive mixer. So, now the LO will be balanced. So the here there is a LO and here VLO bar and there is a RL. So this is a single sideband version of the, this is VRF. So this is a single side version, single balance version of the passive mixer where RF is the input and then VLO has a differential input. The gain for the same is 2 by pi, and if we try to make it a double balance of the same, so double balance is given by, so this is a double balance version of the same. So here what we can do is we connect this to this to this, and then this is a RL. This is VLO, VLO and VLO bar. This is VRF, VRF bar. So in the double balance it looks like a same differential Gilbert cell mixer that we have seen. The only difference is here the only there is a LO which is a switch in the MOSFET. It's RF signal whatever is coming is a switched and you are getting a differential differential signal. Now when you are making the double balance version, it will help us to cancel the feed through, LO feed through, because the current as I discussed in the last class, there is a constructive interference for VRF and destructive for VLO, and it will reduce the LO feed through in a double balance. However, there is a significant feed through of LO in a single balance mixer. So the gain will remain same because you are giving a differential input, again you are getting the differential output. So that is why the gain will be 2 by pi. Now we will try to analyze another kind of mixer, that is a sampling mixer. So in the sampling mixer what we use is a, this is a LO signal and then we use a capacitor. So this can also be, this is a widely used as a, this is, if this is a XT and if this is a YT, this is a sample and hold. Sample and hold circuit. We can use it as a mixer. So let us say if you have a, if you have a XT which is denote something like this, and if I will note with the other color, and if YT, if YT is represented by this color, then initially when switch is on, it will follow the input and then it will hold, again it will follow the input, it will hold, again it will follow the input, then at this point it will hold, again it will follow the input and then it will hold. So, this capacitor is holding the amplitude, and that is why there is a possibility that you might get a little bit conversion gain instead of conversion loss in this kind of mixer. So, this is sometimes this is this kind of mixer is also known as a uh, non return to 0 mixer, as I told. And now if we try to find out the conversion gain of this, we can decompose into the two part, where it is the first is when it is a following, when this is a following like this, and again you will have a something like this, and again you have a. So, entire cycle it is coming down. So, one we follow this, and this is a one y1t, we can consider this as a y1t, and then another y2t, which is a purely square wave, but the square wave amplitude will be different. So, this is at this stage. And if we try to find out the conversion gain with respect to y1t and y2t, if you convolve, if you find the frequency domain and then if we convolve, what we will get is a combination of y1 f and y2 f. If we derive, then we will get combination of y1 f plus y2 f, which is equal to 1 by pi square plus 1 by 4 x f minus f naught plus x f plus f naught, and this will be 0.593, amplitude will be 0.593 x 5 minus f naught plus f plus, and the double. So, if we consider this as a double balance, you will get a twice of this gain. So, if we realize this as a where the capacitor, this is a CL, then we will get a twice of this gain. This is a VLO bar and VRF. We can get the twice of this gain, and it will be higher than the means it is a greater than 0, we will get the conversion gain. However, we can, if we consider the differential version of this, it will give the gain conversion loss, which is 2 by pi only, which is related to the return to 0. So that is for single balance, it can give the point higher gain, conversion gain, but when we consider it as a single balance, then it is uh, going to give us the same 2 by pi loss. Now if we try to analyze the noise of if we try to analyze the noise of the previous, so here we have already got the noise about this, which is a 4 kT RS. Now if we consider the noise due to the RL also, that can be derived as a, so if we also consider the noise due to the RL in that circuit, if this is a on resistance R on, and then there is a switch and there is a noise due to RL. This is Vin out. Now Vn out square we can write, because this output noise is given by equal to 2 kT here R on parallel RL plus RL, and if R on is much less, you can write this as a 2 kT RL. Now if we want to find the input referred noise, so as we have seen input referred noise, so input referred noise is given by Vn In square, that we need to divide it by gain, so that is 1 by pi square. So that is 2 kT RL, that is 1 by pi square, because if we consider the single ended, when the signal is a single ended down converted at omega plus omega naught and omega minus omega naught, there is a 1 by pi and 1 by pi. So that is 1 by pi square. So we will get a 2 pi square kT RL, which is equivalent to 20 kT RL. So this is very important consideration. If you consider the input referred noise, and then if you want to find out the noise figure, so if we take one example, if R on resistance is 100 ohm and RL is equal to 1 kilo ohm, then what is the input referred noise of above circuit? So it is simple, we can write a Vn In square. If we consider the square root, it is 8.14 nanovolt per square root hertz. and if we find out the noise figure, it is given by 10 log of 1 plus 8.14. So we need to consider 2 kT RS also. 8.14 by 0.91 whole square equal to 19 dB, and this is in 50 ohm when we have considered the 50 ohm RS. So you can see that noise figure of mixer is too high, and this passive mixer, because passive mixer does not have a gain, it has a loss. So that we need to consider while calculating the noise figure of this, and that is why including the low noise amplifier before mixer is widely used, so that the complete receiver noise can be reduced. We will also discuss about the how we can design architecture which can remove the low noise amplifier, and we can design a mixer first receiver architecture. And mostly in mixer first receiver architecture we are going to use this configuration of the passive mixer. So as we have discussed, the return to non return to 0 mixer. Now we try to find out the noise of the, so if we try to find out the noise of the same, what we need is a, we first make the simple circuit. We can divide in different parts. One is V in, then V in into R1 square, this is a C1, V in out square. So first in this circuit it is a kind of low pass behavior, so we will get Vn. So this is a low pass behavior, we will get Vn out square for low pass filter is given by Vn R1 square mean square into 1 by 1 plus R1 into C of the switch square. So what generally happens, that whatever noise is generated, we have already discussed that if there is any filter, if you have a certain noise and if you pass through the filter, means white noise, if you pass through the filter it will take a shape of that filter. So same thing, it is amplitude is taking the shape of the filter. So here in the second you can see that this is a, this noise is going to switch because of this switch. Now when this is going to switch, you will have a, and this is a C1 capacitor. So what will happen, that you will get a random noise like this, and then after when switch is on it will be constant, again you will get a random noise and then it will be constant. So this what will happen, that you can analyze this noise in two part. One is this only the noise which is switching. And another is that there is a change in the amplitude due to this noise. So, this is a composition, the second composition, and this is a third. So, this is the first. While calculating the noise, we need to consider this is the first, second, uh, this is second, and this is a third. So, if we try to write it down the each noise, so Vn1 square, we will get Vn1 square. If we consider this is to decompose in the two part, that is Vn1 square, which is given by 2 into 1 by pi square into 1 by 9 pi square 2 kt r1 by 1 plus 2 pi r1 c1f square. So, we can get Vn 1 square f, which is equal to 0.226 2 kt. This is a kt r1. So, at low output frequency, this is a expression because we have considered that our frequency is 1 by r1 into c1. So, this is a final output, that is a 2 kt r1 into 0.226, and this is a two side spectrum. Similarly, we can find out the Vn square for continuous pulse, that is given by a Vn square 2, which is equal to kt 1 by 4 into c1 FLO minus r1 by 2. So, this is how we can find out the noise figure, and the final noise we can write it down in terms of when we add these two, we will get a Vn In square, that is due to the IF kt 3.9 r1 plus 1 by 2 c1 into f LO, and then Vn In square 2 point. So, this is a due to the input referred. If we, this is the output, so this is input referred, two 2.8 kt 3.9 r1 plus 1 by 2 c1 into FLO. So, we can find out the single sideband kt by 2 into 1 by pi square plus 1 by 4, we will get 3.9 r1 plus 1 by 2 c1 into FLO. So, the final noise what we will get is a 1.42 kt into 3.9 r1 plus and if we consider the double sideband, uh, double balance mixer, if we consider double balance mixer, that is given by 2 pi square kt into R1. So, this is how we can find out the noise for the, and this noise, if you see the what we have derived for the capacitor, for the non return to 0 and return to 0, is almost equal, that that is a 2, in the previous case also, that is 2 pi square kt r, and in this case also 2 pi square kt. So, the only difference here, that there is a RL, and in that there is a here there is a R1, which is a switch capacitor. So, this is how we can, and this is, this noise can, if you see this equation, the capacitor is in denominator. So, if you want to reduce the noise figure, then this is a kT by C noise, and if you increase the capacitance, you can reduce the noise. So, this is how the noise calculation you can do in the passive mixer. We will discuss about the noise calculation in active mixer in the next class. Thank you.